Good morning to all. It gives immense pleasure to welcome you all to this webinar on harmonic pollution by power converters and mitigation techniques, hosted by Department of Electrical and Electronics Engineering, Francis Xavier Engineering College, Tirunelveli. On behalf of our management and on behalf of our department, I welcome you all to this webinar. Mr. Govardhanan completed his BE Electrical Electronics Engineering from IPCO Shelang Engineering College, Sivagasi in the year 2003. He completed his post-graduation Power Electronics and Drives from Alagappa Chettiar College of Engineering and Technology, Karaikudi in the year 2005. From 2005 to 2007, he served as a Senior Research Fellow in CVRTE DRDO. From 2007 to 2011, he worked in research and development in ESAP Power Electronic Division. From 2011 to till date, he is working as a technical specialist, Power Electronic and Drives Division in Danfoss Drives Global. During this period, he guided many projects like a design and development of small charge circuit for active front-end rectifier, design and development of modular based drive system up to 1.1 megawatt, design and development of passive harmonic filter and output sine wave filter for variable frequency drives, design support to various projects in variable frequency drives. Apart from this, he is a Six Sigma Green Belt holder for design of products, published many research papers in national and international journals, and published 2 inventions in soft charging techniques of power converters, guided various internship projects in power electronics. We have the sourceful resource person with us. On behalf of our management, on behalf of our department, I welcome Mr. Govardhanan to deliver the webinar on harmonic pollution by power converters and mitigation techniques.
Good morning everyone. Today we are going to discuss the topic harmonic pollution by grid connected power converters and the harmonic mitigation techniques. This is an important topic to be understood by any power electronic or power system engineer. Why we should consider this topic as very important? That can be a question. The answer is to maintain a good power quality at the grid side. Here, what is power quality? The power quality is a concern on maintaining an undistorted voltage at the grid level. Here, the undistorted voltage is due to depends on many factors. The factors are the type of loads connected in the grid, the importance of the grid, the turn on and turn off sequence of the load, the injected current distortion. The injected current distortion is due to the harmonics injected from various type of loads, mainly the power converters. Today, this topic will be towards that one only. Means we are going to discuss all about the harmonic emissions from the power converters. It is important to understand the behavior of the input current and input voltage in a power converter before connecting it into the grid, because the current injection from the power converter, the current harmonic injection from the power converter is going to be the main reason for the voltage pollution at the grid. So a power electronic or power system engineer who designs a power converter should understand a few things. So first, he should understand the grid specification like voltage, current, grid impedance, pre-distortion that is available or existing already in the grid. Second one is allowable harmonic emission from a power converter. The power converter, what is going to he is going to design. The third one is thorough analysis of the type of the power converter and what are all the harmonic limits. The harmonic limits is always provided by different standard authorities. So from this preface, we can start this session. So the session agenda has been sequenced like this. The power factor in nonlinear loads starts from that. Then what is harmonics and measure of harmonics, the effects of power factor and harmonics in power systems, variable frequency drive as a power converter, current harmonics due to variable frequency drives, and international harmonics standard limits, and voltage and current harmonic limits prescribed in IEEE 519. Then different mitigation techniques. Finally, some discussions. This is going to be the agenda for today. Now let us start with power factor. Power factor, first of all, we can understand what is a power factor. There is always a misconception. The power factor is only the cos phi, means the cosine angle between the voltage and current. But this is not only the contributor for power factor. The power factor actually depends on two factors. One is called as displacement power factor, and the second one is distortion power factor. Displacement power factor is nothing but cos phi, as already discussed. But this distortion power factor is due to the harmonic pollution in the voltage and current. So whenever we say it as a power factor, we should consider both these power factor. So we are telling that composed one as true power factor as shown in this slide. So here also we should consider what is an apparent power. The apparent power comprises of real power, reactive power, and distortion power. Here the distortion power is all due to the harmonic pollution. So I hope everyone would have understood what is power factor now. So when you are considering a power factor, you should understand the true power factor, and the true power factor will be accounted for any harmonic analysis. Coming to the harmonics, let us discuss in detail what is harmonics. You can see the various waveforms kept here. You can see the top two waveforms. One is the ideal sine waveform. The second waveform is the distorted waveform. Generally, as of the given sinusoidal voltage, if you are applying into a resistive load, the current will also be sinusoidal. But when the sinusoidal voltage is fed into a nonlinear load or a power converter, the shape of the current will not be sinusoidal, it will get distorted. For example, the waveform will be looking like this, the distorted waveform, whatever shown in this slide. So this distorted waveform can be further decomposed into sinusoidal frequency signals, which will have the order of the multiples of the fundamental. Means you can take this distortion wave and you can decompose it into different frequency sinusoidal signals. While you are composing again those signals, again you can get this distorted waveform. So any waveform can be constructed into multiple sinusoidal waves. So these multiple sinusoidal waves are called as harmonics. So these multiple sinusoidal waves will always be the multiples of the ideal sine wave or the fundamental frequency. So if you are considering a frequency of nth order, if you have a frequency of 50 hertz, then the harmonics produced by this 50 hertz will be the multiple of this 50. So it can be like 100, 150, 200, 250, etc. So you can see how the harmonics are named as. First harmonic means it is the fundamental, that is 50 hertz. Second harmonics is 100 hertz, and so on. So this is how we understood the harmonics. But what is the method to decompose this distorted wave into different sinusoidal frequencies? This is nothing but the Fourier transforms. The Fourier transform method will be used for decomposing into different sinusoidal frequencies. You can use some simulation tools like MATLAB to do this decomposition. You can use the FFT tools in MATLAB. The next slide, measure of harmonics. So there should be a measure for this harmonics, right? So the harmonics, the amount of harmonics in the waveform is quantified as total harmonic distortion. Total harmonic distortion is nothing but it is the dB relative to the fundamental frequency. So you can see the formula here. Uh, the denominator, the fundamental voltage, and in the numerator, it's square of different voltages other than the fundamental voltage. So the amount of distortion is quantified as THD, total harmonic distortion. So if the total harmonic distortion is increasing, then you are injecting more harmonics into the grid. So this needs to be understood. So the allowable limits of THD varies based on the grid impedance by different standards. Grid impedance is always specified in terms of short circuit ratio. You cannot see the grid impedance specified in the standard, but they will specify the short circuit ratio, because the short circuit ratio indirectly refers the grid impedance, because short circuit current is inversely proportional to the grid impedance for the given voltage. Now, the effect of power factor and harmonics in the power system. Here, this slide will discuss what will be the effect here. The listing, it is listing. The first one we can go one by one. The first one is mains voltage distortion. You are injecting harmonics into the grid. So you are injecting a current harmonics into the grid. This current harmonics gives some voltage drop in the grid impedance. So your point of common coupling is getting polluted. The same point of common coupling, the other utilities are also connected. So they are called as neighbor utilities. So the neighbor utilities will face a distorted voltage input because of your pollution. So due to this, there will be a nuisance tripping, zero crossing noise. If there is a voltage detector is there, if it is a then there will be a zero crossing noise, and failure by standby generators. Increase in apparent power, because as I already said, if you are injecting more harmonics, your power factor will become very poor. If the power factor is poor, your apparent power increases for the given power. So the apparent power increases means your equipment will be drawing more current than required. Because of that, you have to design, you have to size the cables and all upstream devices for that increased current rating. So the losses will also be increasing. The third one is damage to the power factor correction capacitors. Reduced capacitive reactance will happen because of the higher order harmonic frequencies. As you all know, the capacitive reactance will be lesser for the higher order harmonics. The fourth one is increased conductor losses. As you are injecting higher order harmonics, there will be a skin effect in the conductor. So the effective resistance will be increasing in the conductor. So the losses will also be more. So these are all few impacts because of the harmonic pollution. So till now we were discussing about the basics of harmonics and their contribution of to grid pollution. And now we are going to take an example power converter which will be polluting the grid. In this case, we have considered a variable frequency drive. The figure shows a typical variable frequency drive, and here it is noted different sections available in the variable frequency drive. You can see here the variable frequency drive derives the power from the mains. There is an RFI filter, the RFI, and then it is a 6 pulse rectifier, diode rectifier, and after that some LC filter. Then the conversion AC to DC happens. From DC to AC, there is a voltage source inverter, which consists of six IGBT switches, and the output will be a variable AC voltage which goes to the motor. Here we can split the variable frequency drive into two groups. One is AC to DC side and DC to AC side, as shown in the figure. If you consider that AC to DC side, it is just a three-phase rectifier which consists of LNC filters. So this is going to be connected to the grid. So in the further sections, we can see how much pollution it is making because of this construction to the grid side. And one more thing to be noted, why we have taken this as an example for analysis. 80%, the VFDs are predominant in predominant devices used to be connected to the grid because they are rated they are always rated high power. It ranges till 1.10 megawatt also. So the pollution is mainly due to majorly due to VFD kind of converters, and 80% of the VFDs in the market have three-phase diode rectifiers in the front end. So this example is considered. This will be very helpful for understanding the harmonics and the effects of harmonics at the grid and mitigation techniques. Now we can see what is the current harmonics injection because of the variable frequency drive. As I already said, we need to consider the front end, means the three-phase rectifier, and how it is injecting the harmonics into the grid. According to the principle of the three-phase rectifier, input current is not sinusoidal in nature. Even though there is a resistive load at the output of the three-phase rectifier, you will not be able to see a sinusoidal waveform, sinusoidal current at the input side. Already it is distorted. So as I already mentioned, if the current, if the shape of the waveform is not sinusoidal, then it means you are generating more harmonics. So considering that, already you started polluting the grid. Second, you are seeing one bulk capacitor at the DC link. This, as you are adding this DC link, the current will further get polluted because the capacitor will store the energy and deliver the energy to the inverter side. So you can see in every cycle, you will see a distorted current waveforms like this. The waveforms have been shown here, IA, IB, IC. They are the currents at the main side. You can see it is not sinusoidal, it is discontinuous. And if you are doing an FFT for this waveform, you will be seeing huge harmonics at the grid side. So let us see how the harmonics are. Here, the current harmonics for a typical variable frequency drive without any harmonic mitigation is shown here. The first waveform what you are seeing is the fundamental. So the fundamental current, and the last waveform whatever you are seeing, it will be the actual current at the three-phase rectifier's input. So if you want to reconstruct the third waveform into the first one, you need to add the middle one, the second waveform. So the second waveform will be the distortion actually. As the second waveform is added to the first waveform, you are getting a distorted waveform like the third one. So what I am going to do is I am going to decompose through FFT this third signal. While we doing like this, I can get a result like this. You can see the fundamental current is 38.57 ampere. The total harmonic distortion is 104.52, and the RMS current is 55.79 ampere. So you can see here you have a lot of harmonics present here. So if I am decomposing into harmonics, actually, you can see fifth harmonic is 30 ampere, seventh harmonic is 23, 11th is 10, and 13 is 5.07. Because these are all the predominant harmonics always present when you are connecting a three-phase rectifier into the grid. So the mitigation should always be focusing on eliminating these harmonics. We will be seeing in further slides how these harmonics are eliminated through different techniques. But this is how we should understand the harmonic pollution because of a three-phase rectifier. So there can be a question: who will be how to design a power converter without harmonic pollution, and what level of harmonics is acceptable? That can be a question. Actually, some international standards are helping us to design a system with the prescribed harmonic limits. So we need to account these factors while we start doing a design of a power converter, the grid connected power converters. So here you can see at different level, different standards are describing the limits for harmonics. At the product level, you can see some different standards from IEC. They are defining the standards. They are defining the limits based on the current rating of the equipment. Similarly, at the utility level, EN 50160 gives the system voltage requirement, how much allowable limits can be there. The third one is at the customer and system level. For example, point of common coupling is given by IEEE 519 G5 bar 4. This is for the UK, and IEEE International and the EN standard for Europe. So they are defining different limits at the PCC level. So now it is something like a simple drawing in a grid system. You are seeing what is utility transformer. There is ZSC, that is a short circuit, that's a grid impedance. Again, customer utility, again it has own impedance. That Z are the impedance provided by the transformer and cables. And when it comes to the customer level, the customers can connect different loads. It can be a VFD, it can be a motor, anything. Each load will be injecting certain amount of harmonics, which will be injected to the grid. So if you are injecting a current harmonic from a VFD, that goes and drops in the impedance actually. So if you are seeing once there is a voltage drop across the first unit, then you will be getting a polluted waveform at the PCC level. So this is how the analysis need to be made when you are connecting an equipment into a utility. Here this slide shows what is the voltage and current distortion limits prescribed in IEEE 519. The first table shows the voltage distortion limits at different bus voltages and what should be the individual harmonic limits and what should be the total harmonic distortion. So this is the main aim actually. Whatever you are doing, you have to maintain the voltage distortion limits at the PCC. So to maintain the voltage distortion limit, how extent we can inject the current distortion, that is prescribed in table 2. Here, as I already said in the preface, there are different THD limits or TDD limits here in the last column with respect to different short circuit ratio. This short circuit ratio is nothing but ISC by IL. ISC is the short circuit current at the grid, and IL is the rated load of the equipment or demand current. You can tell like that. So this gives the short circuit ratio. So each short circuit ratio will give a different limits for TDD and different order of harmonics here. You can see. So this is the limit prescribed in IEEE 519. So if you are going to design a power converter, you need to consider these limits and you need to add the relevant mitigation techniques to meet the harmonic standards. This is one of the example. The similar examples, a similar way, the other standards are also prescribing based on the regions actually. So now into different mitigation techniques. There are 6 mitigation techniques are available here. They are commonly used. We are going to discuss today. The first one is adding DC chokes in the DC link. Second, adding AC reactors. Third one is passive shunt filter. Fourth one is active shunt filters. Fifth one is active series filtering. Otherwise, it is called as active front-end rectifier. The sixth one is multipulse rectifier. All these mitigation techniques are listed down considering a three-phase rectifier only, means the VFD 6 pulse rectifier. We can see one by one. The first one is adding DC chokes. You have seen in the earlier mail how the current got polluted because of the DC capacitor. The DC capacitor makes the grid current very poor. So by adding a filter in here like this in the DC link, it's an inductor. The TSD level can be reduced. Then the current will be reconstructed into somewhat better level. So if by doing this DC choke connections, we can limit the TSD level to 35 to 40%. Here we are seeing very nominal voltage drop because as we are adding it in the DC side. Here the major current flowing through this inductor will be DC. Only minor AC current will be flowing. They are the ripple current. If you are considering the drop across the inductor, it is always due to that minor AC currents, because we know very well the drop across the inductor is due to alternating current only. So normally the VFD manufacturers used to offer as a part of the drive. So second mitigation technique is adding AC reactor. Here we are not seeing DC reactor, but AC reactor is added. Here by doing this, we can get the similar limits 35 to 40, but there will be a considerable voltage drop. As I already mentioned, here these inductors will be facing only AC current. So the drop can be varying from 1% to 3%. Many drive manufacturers are offering as a part of the drive, because this gives one more advantage actually. So if there is a grid disturbances, it can protect the diode rectifier from the grid disturbances. So instead of having the line reactor in DC side, the other preference could be at the AC. So this is good for grids with low impedance. Yeah. So this is the second technique. The third one is passive shunt filter. The earlier two techniques can limit the TSD only up to 30% to 40% actually. This will be okay up to certain level. But if someone wants to meet the IEEE 519 standard, then their need is to reduce the harmonics very less. So how to do that? The further slides will be showing some of the mitigation techniques which will be helpful to meet the IEEE 519 levels. You can see this is one of the technique, passive shunt filter. I already mentioned you, whenever a three-phase rectifier based VFD is connected to the grid, the VFD will be emitting majorly fifth harmonic, seventh harmonic, 11th harmonic, and 13th harmonic. They are the major harmonics that will be injected to the grid. So if we are eliminating these four harmonics majorly, then automatically the waveform will be reconstructed into a sinusoidal waveform. So the passive shunt filter, it's a kind of a trap filter. Means it's a kind of, you can consider this as a notch filter. So notch filter is, there's a band pass. So you can tune the filter into a certain frequency. So if you tune this filter for the specified 5, 7, 11, and 13 harmonics, then they will be trapping those frequencies, and it will reconstruct the grid current waveform into sinusoidal. So they are called as trap filters also. Here I have shown only one section, only one notch filter. So this can be designed for eliminating the fifth harmonic. So if you want to eliminate, for example, 11th harmonic, you need to add one more notch filter, which is tuned for the 11th harmonic. So this is a simple approach for eliminating harmonics actually. You can see the waveforms here. You can see the drive side current. It is a pulsated one as shown here. But after adding the filter, you can see the grid current became sinusoidal. The first waveform shows close to sinusoidal current at the grid side. It is a compact solution and robust for environments because there is no active components involved here. And there is some disadvantages like leading power factor at partial loads, and design is load dependent because the tuning should be done for the filters considering the available LC component inside the drive. So we need to understand the drive and we need to tune this filter LNC values. The other technique which will be used for meeting the IEEE standard is active shunt filters. Active shunt filters is also a filter which will be connected in shunt, similar to the passive shunt filters before the grid. Here you can see the mitigate this unit will have a bulky capacitor that as here it is shown as CDC and F. So this is the capacitor. It stores the energy, and this capacitor will be switched in fashion such that the current will be injected into the grid as a compensating current. You can see the waveform here. The drive current is supposed to be like this, the first waveform. So if you are injecting the filter current in the like the second waveform, you can reconstruct the grid current into a sinusoidal one. So the drive current will be non-sinusoidal and the grid current will be sinusoidal. So the difference of grid current and drive current will be injected by this active filter. So this active filter normally senses the polluted current at the at the drive side, and it will inject the required harmonic currents to reconstruct the waveform into sinusoidal at the grid side. This is what it is doing. But this one needs filter. This one needs a 6 pulse converter like this. The IGBT converters is here, and there is an LCL filter. So with this construction and the control circuits, it will be switching the IGBTs in the fashion to inject the current as required. So it is more adaptive based on the load. Actually, if the load is also varying, according to that, it will correct and then it will adjust its injecting current. So it is sizable to meet demands. It has a retrofit solution. So if there is a failure, we can remove this and then we can put a new one. We no need to disturb the variable frequency drive. Shoots for group compensation also. Not it is not only VFD, some other polluting load if it is connected. This active shunt filter is capable of mitigating that harmonics as well. Here we can see the only disadvantages: the reduced overall system efficiency, as well as if you are considering the cost, overall cost compared to the passive shunt filter, the active shunt filter will be more expensive. The third method to meet IEEE 519 is active front-end rectifier. Active front-end rectifier. As till now, whatever you are seeing is a diode front-end rectifier. Here you can see that IGBT front-end rectifier. So the advantage of you can see it is looking like an inverter, VSI inverter at the input side also, with some LCL filter at the front end. So Here you can see uh, the IGBTs can switch from AC to DC section also and DC to AC section also. So the main advantage of this with respect to variable frequency drivers, if there is a regenerated energy from the motor that can be supplied to the grid, because this will be acting like a bidirectional converter. Here, additionally, these IGBTs will be switching in a fashion to reconstruct the distorted waveform into a sinusoidal one. Here it will be acting in a boost mode. So we will set a limit for at the DC link voltage, and whatever voltage seen at the input voltage, which will be boosted to the DC the set voltage actually. During this process, the current will also be reconstructed into a sinusoidal waveform. The switching will be managed by this IGBT. By doing this, the current waveform will be maintained perfectly at sinusoidal to meet less than 5% total harmonic distortion as prescribed in IEEE 519. Here, there is no retrofit, but it is a part of the drive. So it is a compact installation, and it is used for large single drives, systems with high load dynamics, low load and grid dependent. Only thing is low efficiency because a lot of switches and the switching losses should also be considered here. And the cost involved is also high because there is a LCL filter at the input side, and there are control circuits also available. If it is a diode rectifier, these things will not be present. So considering this IGBT bridge, the cost will be increasing in the variable frequency drives. The fourth technique to meet IEEE 519 is to use multipulse converter. This is a traditional technique. So you might have learnt about the 12 pulse transformers and 18 pulse transformers. 12 pulse transformer, in the sense, there will be two rectifiers. They will be connected in parallel. One rectifier will be connected to a delta secondary winding, and the other rectifier will be connected to the star secondary winding. The voltage from the secondary windings will be displaced by 30-degree angle. So when these two rectifiers will be conducting variably, but considering the primary current, you there will be a because of this phenomena, you will be getting a more close sinusoidal waveform. So once we reconstruct this waveform into sinusoidal, automatically what happens is your harmonic distortion at the PCC level is getting corrected. So this is how the 12 pulse. So the multiples of pulses will reduce the harmonic frequency. Already we know. So the multiples will grow like 18 pulse, 24 pulse, something like that. So you can see the harmonic current analysis in the bottom. The 12 pulse, the fundamental current is 36 ampere. The total harmonic distortion is 10.68. But when it comes to 18 pulse, it is 8.9 only. So if the pulse number increases, then you will be getting reduced current harmonics, reduced THID. So here, this is a robust and simple technology. No resonant point issues, low cost solution, because then high efficiency. However, even though there are some advantages, there are disadvantages also in these techniques. Load and grid dependent performance, less performance in unbalanced grids, because in balanced grid it works good, but if there is an unbalance based on the load and based on the construction, the harmonics will vary. And the load and grid dependent performance, as I already mentioned, load will affect the harmonic levels, and the grid dependent grid impedance will also play an importance actually here. So these are all the different techniques that can be used to eliminate the harmonics produced by a 6 pulse variable frequency drive. So here today we discussed mostly the three-phase rectifier kind of power converters. But if you are considering any other power converter that is going to be connected to the grid, the same kind of analysis need to be made. First, we need to know what type of converter it is and what kind of waveform it can generate at the input side. Then we need to do an FFT to understand the level of harmonics. Then we need to identify what are the limits prescribed in different standards, considering where you are going to connect this product. After knowing all these things, you need to identify the right mitigation technique for eliminating those harmonics. This is how a design process need to be done if we are going for a power converter design and the mitigation techniques. This is how we are closing this session. Thank you. Thanks for your attention.
Thank you, sir. Good afternoon, everyone. It's time to show the gratitude. I'd like to thank God Almighty for His guidance and support in organizing this webinar. I'd like to thank the resource person for his wonderful speech. I'd like to thank the college management, the chairman, vice chairperson, managing director, general manager, principal, and all the M team people for their continuous support. I'd like to thank Dr. P. Annapandi, Head of Electrical and Electronics Engineering, for his motivation and support. I'd like to thank the fellow coordinators, Dr. A. Ravi, Mr. J. Anthony Robinson, for their dedication and hard work. I'd like to thank all the participants for their involvement and active participation in this event. Thank you, one and all.